Hey everybody, it's Ripley. All right, we're going to go ahead and finish up this chapter. We're going to talk about the binomial. We're going to revisit that guy because something funky is going to happen. The binomial approx to the normal curve. Now, this may seem like way out in left field. It's like, wait, we just did all this cool stuff with the normal curve and sampling distributions and the central limit theorem, and we got this new formula for finding z for sample means, rather than just for individuals out of a population where we know what the shape of the distribution is. Boy, I just summed up about the whole semester, didn't I? And all of a sudden you throw in a binomial approximation of the normal. Well, let's just stop for a second. Let's revisit what binomial means. We know that n is the fixed number of trials. All right. We know that x is, what did we say? N is the fixed number of trials. X is the number of hits, right? Remember how that worked? P is equal to the probability of a hit, prob of a hit. You're writing terribly. And Q, which is 1 minus P, equals the probability, just because we can use the complements, probability of a miss or a not hit. Whoa, a miss. Oh, you're going to have to bear with me. A miss or the complement of a hit. All right, right? So we know that the probability that X equals big O X, where big O X is just a number, we're not afraid, right, is just n choose big O X, P to the X, Q to the n minus X. Okay? Now, just a quick little refresher for those of you that, that may not remember that. Now, I'm going to show you something. I'm going to use an applet to show you something that's pretty cool. All right, so I'm going to escape out of here and we'll go look at this applet real quick. Okay. Now, n is the number of trials, right? It's the number it's the number of outcomes that we can possibly have, right? That makes sense? So remember, n was like, what did we talk about? Oh, we did this, the number of Big Macs that come out in n cars, or excuse me, in 10 cars. So it could be 1 Big Mac, it could be 0 Big Macs, 1 Big Macs, 2 Big Macs, etc., etc. Sorry guys, I'm a little distracted. There's some construction going on down here. So hey, yeah, let's do that. Let's talk about, what did we do? We did 10 cars. I think we did 10 cars. And we said the probability of a Big Mac was 0.7. And then what I'm going to do is I'm going to do something very much like a sampling distribution. Okay, I'm going to do this. I'm going to show you real quick. I'm going to do this 1,000 times. All right. So think of this as I watch cars go through a drive-through 10 at a time, and then I do that 1,000 different times. All right. And let's simulate this, and I'll show you what happens. All right. Now check it out. What does that look like to you? It almost looks normal, doesn't it? It almost looks perfectly normal. In fact, remember, the maximum number of cars that could get a Big Mac was 10. If I could just extend this guy a little bit further, it would probably look really close to normal. Now, let's make sure we read this correctly. Remember, I sampled 10 cars at a time, randomly, and then I watched this happen. I did that process 1,000 times. All right? None of the times, there were no times that of the 10 cars, nobody ordered a Big Mac. There were no times that only 1 out of the 10 cars ordered a Big Mac. There were 4 times that 2 of the cars out of the 10 ordered a Big Mac. There were 7 times there were 7 times when 3 out of the 10 cars only ordered 3 Big Mac, or ordered a Big Mac. Wow, it's a lot of numbers floating around, isn't it? 28 times when 4 out of the 10 cars ordered a Big Mac, etc., etc., etc. Notice, got a nice high spike right here, which is, we know that's got to happen, right? Remember, the mean is n times p. It's going to be right here in the middle of this thing. Now, watch this. Watch what happens if I change the probability of ordering a Big Mac from 70% to 50%, or 0.5. Watch what happens. Ooh, yeah. Look at that. Isn't that cool? Now, if I simulate it, remember, these are random samples. So it's going to change, but they all look very normal. Now, what happens if n equals, say, 25? All right, now think about this. I'm now grabbing 25 cars at a time. Now, instead of 0.5, let's do 0.6, just for giggles, okay? And instead of 1,000, let's do 100. Watch what happens. Whoa, that looks strange, doesn't it, right? So remember, we've got 25 cars, and this is the grouping around the number of Big Macs that they order, okay? Instead of 100, let's do 1,000. Watch what increasing the number of times that you do this, think of it as sampling distribution, right? Does to, whoa, just like that. You got yourself a normal curve. Now, it's clearly not normal because a normal curve is a continuous function. Remember how we defined that sucker with that awful e to the negative x minus mu squared over 2 sigma squared? It was that awful formula. And these have discrete values. These have discrete values. It's not like our normal curves where we had continuous values, right? If we take the heights of women, they can have any value theoretically between 0, that's a small woman, and 900,000 feet tall. If that were true, I would be in trouble. All right? I have a very tall girlfriend, but she's not 900,000 feet. Okay? Etc. You see how this works? Look at the difference. This is on a continuum. The area under the curve is 1. This is not. However, if I add up all these values, remember when I did it before, what did I do? I did 10, and I did 0.7, and I did it 1,000 times. If I add all these values up, I get all 1,000. All right? I get all of the possible combinations that could have happened. Okay? So what we have is an approximation to the normal curve with this guy. Okay? Now, if we have an approximation to the normal curve, that's the second time I've done that, then what am I allowed to use? What sucks everything down to every normal curve, or excuse me, to the standard normal curve? We have a z-score, okay? And the z-score is, what is it? It's x minus mu over sigma. Now, this is where it gets a little bit crazy because we actually know that if we're looking at sample means, then it's x bar minus mu over sigma over root n. But because we're talking about the binomial approximation to the normal curve, what we're really talking about is this x right here is the same x is over here. Okay, now let me show you. We're not panicking. Hopefully you remember from when we talked about the binomial curve, excuse me, binomial curve, the binomial probability distribution, you remember that mu was equal to, remember how that worked? It was just NP. And sigma was equal to the square root of NP cubed. Remember how that played out? Now wait, if mu equals NP, and sigma equals NP cubed, we are so golden. That's the coolest part, right? So all I have to do is use this formula. Now, let's go back to, excuse me, let's go back to the Big Mac problem real quick.